Okay. Hello, everyone. Thank you for coming to our presentation about monitoring of the OpenStack services, and not only. Technical difficulties.
Weird.
Perfect. So my name is George Mihescu, and I'm with my colleague Jared Baker here today. I'm the cloud architect for the Cancer Genome Collaboratory. I have about 7 years of experience with OpenStack. I first deployed OpenStack during the Cactus release, and I went to the first public conference in Boston, 2011. And I also was a speaker in Barcelona, Boston, and currently in Vancouver. And Jared's gonna...
Yeah, my name's Jared Baker. I've worked in the IT industry for about 12 years now. 2 years have been with OpenStack, with George in the Cancer Genome Collaboratory. First deployment was Liberty, and my first conference was a year ago in Boston.
I'm going to give a little bit of introduction about OICR, Cancer Genome Collaboratory, before going into the monitoring part of the presentation. So OICR, Ontario Institute for Cancer Research, is the largest cancer research institute in Canada. It's funded by the government of Ontario, and we support about 1,700 researchers and trainees doing cancer research across the province. Cancer Genome Collaboratory is based on a research grant that had the goal of building a cloud environment specially crafted for cancer research by OICR, and as I said, funded by government of Canada grants. It enables large-scale cancer research on the world's largest cancer genome data set. About 700 terabytes that we currently have, cancer research data from patients all over the world. We have data about 50 most common types of cancer with data sets collected from multiple countries for the same type of cancer for better coverage. And it was built entirely using open source software like OpenStack and Ceph. The grant goal for infrastructure was to build a compute environment capable of supporting 3,000 cores and 15 petabytes of genomic data. And we also had to build a system for cost recovery in order to make this project self-sustainable. We employed a no-frills design. So because we had a fixed budget and high requirements for deliverable, we used high-density commodity hardware in order to reduce the physical footprint and related overhead. As I said, we used only open source tools, so no licensed software is used in Collaboratory. We prefer to use copper instead of fiber for cost reasons, and we didn't have a latency requirement. And we spent, as I said, 100% of the infrastructure budget on capacity for research, not on nice-to-have features or support from vendors. This is a standard layout that we use. We have 8 storage nodes at the bottom, high-density storage nodes used for Ceph. And we have 4 high-density compute chassis. Each of them has 4 nodes, so we have 16 compute nodes per rack. And 2 WAN switches at top. One is a 48 gig production switch. The other is 48 1 gig ports for out-of-band. And the compute nodes have 40 cores, 10 gigabits network connectivity, 256 gigs of RAM. So they are basically designed to deal with the very intensive CPU workloads and high memory requirements of the genomics research. On the storage side, we have 34 storage nodes, more than 1,200 OSD drives, different sizes, because we grew the environment over time. When we started, we acquired the 4 terabyte drives. Next acquisition, it was 6, 8, 10 terabytes. So we have a mix of storage nodes. And currently, we have 7.6 petabytes of raw storage. About 2 petabytes are used to store the very large genomic data sets. On average, DNA sequenced a line about 150 gigabytes. So we have these very large files uploaded in Ceph as objects. And we customize Ceph to deal with very large files. And on the storage nodes, we have 4 10 gig networks. We have 2 10 gig networks bonded for client traffic and 2 10 gig for replication. We use a highly available control plane. We have 3 controllers. We have plenty of CPU, RAM, and we have very fast SSD drives used just in the controllers. And we have, this is actually the second design. The initial design had 3 separate RAID 1 containers. Now we have just 1 RAID 10, and we have different LVM partitions for different use cases inside the controller. So the operating system has an LVM that you can grow, and Ceph Mon and MySQL the same. We use HA proxy for load balancing. We keep alive diff for moving the internal and public VIPs between the controllers in case of failure or shutdown or maintenance. We use ECC certificates from Let's Encrypt in order to reduce the load for encryption decryption of the SSL traffic, very large downloads happening through the HA proxy. And on the controller side, we have also 4 10 gig networks that we bond together, and we have VLANs on top of them to separate different types of traffic going to the controllers. On the network side, we use Neutron, GRE, and HA routers. So we have every project has a router that is highly available with 2 routers across the 3 controllers. So each controller has active passive for a number of Neutron tenants. And we don't use DVR for Neutron. On the networking side, the physical layer, we have Ruckus, which is the old Brocade switches at top of rack. They said 1 EU switches 48 10 gig ports. They have 6 40 gig for uplinks. And we create a stack, which is a ring. So ring rack 2 connects to rack 3 and rack 1, and so on. And we close the loop with fiber because the distance is too far, so the twin-ax cables do not allow for more than 10 meters. So we close the loop between rack 1 and 6 with fiber, but everything else is twin-ax cables, which are very inexpensive compared with fiber. And we also have an oversubscription ratio of 2 to 1. So we have 480 gigs going to the servers in the rack and 240 gigs going outside of the rack. As I said, modern cancer research basically relies on large-scale studies because of the extreme diversity of the mutations. So we decided that capacity was more important than speed when we designed Collaboratory. Being able to run more workflows and analyze more data gives researchers more confidence that the insight provided is correct. You cannot just analyze 3, 5, 10 samples and draw a conclusion. You have to do many more until you confirm that's the conclusion you can draw. So capacity is more important than performance. We can always upgrade the slower parts of the system as the cost of technology goes down. So anything you build today is going to be only cheaper 6 months down the road. We started in 2014 with Juno. We upgraded 7 times. We upgraded to Pike a few weeks ago. Ceph, we started again with Giant and Hammer and Jewel. We loaded data in the cluster over time. Now we have about 670 terabytes of very large protected data sets. We also went through an operating system upgrade for the compute nodes and controllers, and actually the storage nodes as well, from 1404 to 1604. Went fine as well. Now we go into the monitoring part of the presentation. So we use a number of tools for operating the cluster. Openstack and Ceph are the main core components, and of course Ubuntu for operating system, but Ansible for configuration management, Zabbix for the main monitoring and alerting tool. Have an ELK stack also for monitoring and alerting and log aggregation. Sflowtrend allows us to see live traffic going through the top-of-rack switches and to the internet. We use Rally intensively for automating testing of the environment. What we do with Rally is very interesting because Rally allows us to do every hour end-to-end tests. So we have a cron job that calls a Rally test that starts an instance, assigns a floating IP, SSHs into the floating IP, then it pings a host on the internet, like Google, 5 times. It captures the result and then exits. And then if the check fails, or it takes too long, longer than the threshold we set, or if the packet loss from the 5 pings is higher than a threshold, we get an alert. At the end of the script, we have set the runtime of the test to be sent to Graphite, and then use Grafana to see over time how long these end-to-end tests take, and we see if it takes longer, it takes less, what's the trend in our environment. Similarly, we use Rally to test RBD volume performance. So we start an instance from a volume this time, and floating IP assignment happens, SSHs, and then we run a DD test of the 10 gig file 3 times in a row. We calculate the average time, and then we send this average time to Graphite, so we can see on an hourly basis and aggregate in an average how long it takes to write a 10 gig file against a Cinder volume backed by Ceph. This is an example of Grafana dashboard that shows the Rally ping test. You see takes between 50 seconds and 1 minute, depending on the load on the cluster and what else is happening. We also boot from a volume just to see that booting from a volume works. And then the Ceph write test that actually does I/O operations against the RBD volume. This is a Rally smoke test that we perform once in a while and mandatory after each OpenStack upgrade. And it's a 500 instances creation in batches of 50 or 100. And we see, first of all, if we have any error rate, see how long it takes on each step of the instance boot process. It allows us to basically confirm all the APIs function normally after the upgrade at the load test. Because just starting an instance doesn't mean that it's going to work fine when you have 100 started at once. We like Zabbix and Grafana because Grafana can use Zabbix as a data source. So we collect a lot of data with Zabbix. Data goes into Zabbix is a MySQL database, but Zabbix has a new UI that sometimes is not as flexible and maybe nicely looking as Grafana. So we can set Grafana to use Zabbix as a data source, and that allows us to have the same data graphed twice. In this case, we have the internet graph, basically the data points displayed in 2 different tools, but also it allows us to put in the same dashboard in Grafana multiple types of information. In this case, we have the Rados gateway traffic compared with the CPU usage on the controller, and as well with the memory, RSS memory usage for the Rados gateway process. So we can see that there is a correlation between how much data we push or pull through Rados gateway, its memory usage, and CPU usage. So we can do these things because we use Zabbix as a data source in Grafana. We Dockerized parts of our monitoring stack. Mainly we use Sflowtrend. They provide the Docker container. We use Prometheus, Graphite, and Collect D and Grafana in one tool. Elasticsearch was recently Dockerized, so we use Elasticsearch, Logstash, and Kibana. This is how we move to the latest version of Kibana and Logstash and Elasticsearch. And this allows us to basically upgrade easier and not overload the system with installing packages every time we have to upgrade. Just pull a newer container. We use Ceph Monitoring. It's a Docker container provided, and it pulls information about the volumes. And I find it very interesting to see how Ceph is loaded by different types of applications. So as you can see here, the IOPS for the volumes pool is much higher versus the Rados gateway, because we use 64 meg Rados blocks for the Rados gateway pool because we have very large files. When somebody downloads a 150 gig genomic file, that puts very little pressure on Ceph I/O wide. Compared with somebody who mounts, attaches an RBD volume and does maybe 4K I/O, causes much more I/O activity than very large download. And in our Ceph cluster is predominantly used for reads from the object storage. We have a small pool in Ceph allocated for volumes. Most users basically start VMs that boot from the local disk of the compute nodes. The compute nodes have very large disks. We have 6 2 terabyte drives per compute node in array 10. So we have about 5.3 terabytes of local disk. And the VMs are very large. Genomic VMs have about 8 cores and 48 gigs of RAM. And usually we run 3, 4, 5 VMs per compute node. So when they do I/O and is a hotspot in the cluster, that is local to a compute node. It doesn't impact the Ceph cluster. We don't need the SSD for the journals for Ceph because we upload the data and then the data is downloaded directly from the primary replica. Latency is not a requirement for this kind of workloads. Plus, for 36 drives per storage node, going with the recommended 1:6 ratio for journal, then you would waste about 20% of space to have SSD drives that are just providing you fast writes until they have to flash, and then you have to wait anyway. So it's not very cost efficient for our use case. This is another Grafana dashboard where you can see the Ceph hourly download. So we store these very large data sets, and the researchers download the files to the VMs and analyze them automatically. So we want to test the performance of this download. So we have a VM that hourly picks a random file from a predefined list of files that have a very similar size, between 100 and 100 gig files, in size, and download the files. And then we see how long it takes to make this download and send the data to Grafana. So we can see on an hourly basis if the experience of a researcher who downloads the data from the cluster is better or worse, or how is over time. And this helps us also with the Ceph upgrades. The entire environment is basically tested hourly, and we keep long-term graphs. Another thing we do is we run a script that for each project looks at the quota allocated and how much quota is used and sends this percentage to Grafana, so we can see anytime if a project had a spike in the middle of the month maybe and now it went down, or if they always run at 100% capacity, so we can proactively contact them and see if they want a quota increase or if it's a dormant project. It gives us a long-term capacity planning tool. And as I mentioned, Sflowtrend, we recently added to our environment, and it allows us, the free version of Sflowtrend is basically an Sflow collector. We have the top-of-rack switches that are stacked, so they only show us as one Sflow generator, and sends data to Sflowtrend running in Docker, and we can see up to an hour of live traffic going through the entire top-of-rack stack. Okay, so we can see if somebody is downloading or doing a lot of traffic from the internet, we can pinpoint where it's coming from through all the active flows going through our network. I'm going to hand off to Jared now to continue.
Thanks, George. All right, so let's talk a little bit more about some tools. So Zabbix is at the core of our monitoring. It's doing the bulk of the monitoring and alerting for basically everything. With 225 hosts and over 38,000 items monitored, our deployment would still only be considered like a small to medium in terms of a Zabbix deployment. And even that just consumes a minimal amount of resources to run. So we like it, one, because having never seen it crash before, it's pretty reliable. And two, it's very performant. Three, it's easy to upgrade. 4, it's customizable. So we can build in a lot of OpenStack specific checks. For example, if one of our OpenStack APIs goes down or the dashboard is slow to load, we can be alerted through a descriptive email or Slack message. And on all of our servers, we've installed the Zabbix agent, which enables us to get a ton of information about the server. So not only can we monitor certain things about OpenStack, but we can also keep an eye on many things important to us in an environment such as power usage or smart data and even temperatures. And this screenshot here was a recent cooling failure event. And you can see for this particular rack, all the devices went up about 25 degrees Celsius before everything shut down. So that was not fun. And we also have some in-house scripts that can be written to work with Zabbix. For example, we use Ceph RBD as a backend for Cinder volumes, and we have seen these two go out of sync before. So we wrote a script that uses the OpenStack client to list and count the number of Cinder volumes, and then also use the RBD client to do the same thing. And the script can do a comparison to find anything unique and then outputs a simple Boolean status that Zabbix can easily understand, and you can build a trigger to work for. Now, for every OpenStack API, we have checks that use the Zabbix agent to verify if the process is running, and that the required TCP port is listening on the host. Now, this is a good start, but just because the process is running and the port is open doesn't mean that the service is functioning correctly. So we also need to make some API calls from somewhere externally. From our monitoring server, we can have Zabbix call a script to perform an API call. For example, to check the Nova API, the script may issue the equivalent of an OpenStack server list and monitor the response from the API to ensure that the call returned to status 200. So using the Zabbix agent, we can also monitor the amount of RAM certain OpenStack services are consuming. We can monitor the memory utilization over time, and we can set up the alert thresholds for high memory usage, which could be triggered by a memory leak. And having these historical graphs allows us to see what impact, if any, an OpenStack upgrade might have in memory utilization over time. So we monitor the Neutron router traffic, and this has been particularly challenging as our routers are highly available, like active and standby, and the active router and such traffic may move from one controller to another, depending on network events. So we also have to deal with projects coming and going, which means monitoring new routers and retiring data for old routers. A solution for this was to use a discovery rule, which is a Zabbix feature that runs once an hour to find new QRouter namespaces on each controller. Once a new namespace is discovered, Zabbix automatically starts polling the send and receive values of the router's interface and creates graphs for that data. And from there, we have a dynamic Zabbix screen, which is populated dynamically with each router and allows us to look at the router traffic easily. We can also use Zabbix for capacity planning. Since we monitor the trends of items, such as the number of allocated vCPUs and VRAM cluster-wide, we can predict when resources might be exhausted and plan for any expansions. And when it comes to alerts and triggers, we have Zabbix sending to two places, email and Slack. Slack is particularly useful for its mobility and flexibility to display alerts in a short and concise manner. We also have the ability to send Slack alerts to different channels, which can be useful for collaborating with other teams. So an OpenStack environment generates a lot of logs, and some of the information in those logs is extremely useful for monitoring of performance, problems, and other analytics. So we install Filebeat clients on all our servers, and they ship specific logs securely to our Logstash server and then into Elasticsearch. And once the logging data is indexed in Elasticsearch, we can use Kibana to build meaningful visualizations, such as this one, which gives us statistics about the Nova API. We run these services, as George mentioned, in 3 different Docker containers and manage this particular collection of Docker containers with Docker Compose. and then the Filebeat client is installed natively on each server. We try to maintain about 90 days of logs, and that's usually around 120 gigs. And we can prune indexes automatically with the Curator tool, which is another Elastic product. So this is one of our more useful dashboards, as it has some basic statistics about what is happening in the environment. And we can see how many instances are being created and terminated based on your timeline in Kibana, as well as the distribution of logs amongst various services, files, and hosts. And do we have any Nova or Ceph errors recently? Any failed SSH attempts to our servers? We can see how much is being downloaded from our object storage with a simple metric visualization at the bottom there. So with Filebeat being the log shipper, we can define what should and shouldn't be shipped to our Logstash server. So we can do this by picking what files we're interested in, as well as being able to execute certain messages or keywords within each file. So dropping certain messages at the client from being shipped helps reduce the network traffic and load on our Logstash server. So another Filebeat feature that we found useful is the ability to tag some of these log files. So for example, we can tag all glance log files with the tags glance and OpenStack, as in that slide there. And we can take all the heat log files and tag them with heat and OpenStack. And this just makes it really convenient in Kibana, as these tags can be used for searches and filters and visualizations. Here's another dashboard which we created to show us web analytics for the OpenStack dashboard. We can see who's trying to log in, what their IP is, and using the GeoIP plugin, we can plot those users on a map, which makes this kind of cool visualization to see where your users are coming from. We can also graph our HTTP codes over time, which is useful to determine if our users are experiencing any issues with the dashboard, so that sort of thing. So with Logstash server processing all logs coming in, not only can we send them to Elasticsearch, but we can also have the ability to send certain messages as an email or Slack messages to the team. So let's take the following log from a successful login to the OpenStack dashboard. Now we know that logins to the OpenStack dashboard are captured in Apache logs, and there are some fields in the logs that we index, like the login name, the login status, and the IP address. In this example, we've written a query that looks for the login status to be successful, the user to be admin, and an IP address not from our corporate IP space. And finally, the details of an email message if these conditions are matched. So the above log message will match this query because the IP address is not what we expected. And this will trigger an email alert to us if someone logs into the dashboard using the admin account from IP space we don't trust. Oftentimes, it's just George or myself working from home, and our IP isn't recognized in this case. So we also have some transparency or monitoring for our users. So on our Collaboratory website, we have a page for system status that our users can see. This allows us to give historical and real-time status of our environment, including resources. And the back end of this is available on the GitHub repo listed below. So thank you very much. That's all the monitoring stuff I have for today. I'll let George finish off with some of our feature plans.
Thanks. So a few lessons that we learned operating this environment for the last almost 4 years. If something needs to be running, then you have to test it. You can't just expect that it's running. You have to test it. We also were generous from the beginning with the resources for the monitoring on control plane. We are very cost-oriented for the compute and storage because we wanted to bid for capacity, but for controller plane and infrastructure, because it's just a few nodes, we wanted to give them enough resources to be able to grow the cluster without being constrained on this side. We also, I think it's very important to monitor the RAM usage, as Jared said, aggregated per process type. So if you have Nova API with 8 workers, you can add the memory usage, the RSS memory usage for all 8 processes. Another thing that I mentioned, if you have routers running in HA, make sure that have a script that verifies that only one of the layer 3 agents reports that router is active, and only one reports it as standby. We have situations where we have active, or we have 1 active and 2 standbys, or these kind of things. We also have a check now that checks for an IP tables NATing rule in the, for the metadata service inside the QRouter namespace. Just because it should work doesn't mean that it works. Unless you verify, there is no problem in verifying that actually this happens. And also, I think we proved, and by also winning OpenStack Square User today, that it's possible to run OpenStack at a reasonable scale with limited resources and just a few people, as long as you make good choices in design environment and support the projects that are stable and you really need them, and you run a stable configuration for your services. In terms of future plans, we want to add Magnum on Octavia and possibly Trove, so database as a service. We also want to migrate some of our control plane services from Debian packages to containers for ease of upgrade. And our developer colleagues from OICR are working to build a software as a service solution where researchers that are not very familiar with cloud computing, they don't have to start instances, download the data, automate all this with Ansible or other tools. They can just use a UI, select the data sets, select the type of analysis they want to perform, and push a button, and then they get the data, the result into a bucket, into their project's space. And I'd like to thank all the funding agencies for providing the funds for this cloud environment, as well as my colleagues in Toronto. And we are open for questions. Okay.
Where do you find yourself using Prometheus versus the Zabbix collection?
Where?
You mentioned Prometheus was part of your modeling stack.
Yeah.
What kind of use cases lead you to Prometheus versus the Zabbix?
We deployed a while back, but I think the Prometheus container had the integration with Ceph, and that's why you had to use it, because basically it has the code that can extract the data from Ceph. So I'm not sure if when we will upgrade to Luminous, we'll have to find another solution or adapt the existing.
Do you guys share out your Zabbix templates anywhere? Are they upstream open source? Or are you willing to?
Yeah, we are. I mean, on this GitHub repo, we put a lot of the scripts that we discussed today. Some of the Zabbix checks, the templates. We can, I mean, we basically started 4 years ago with, I believe, Mirantis Zabbix checks. Okay, in the fuel plugin, fuel repo, and then added and adapted and so on.
Over time.
So, over time, yeah.
Yeah.
But we can add them to the GitHub. So
that'd be awesome. I'd love to take a look.
yeah,
Cool.
I'd just like to ask how you are getting metrics for hardware rate controller and the fan and CPU temperature. Is it through SNMP, or you guys have some script, or how you are getting these metrics?
Yeah, we use the Zabbix agent, has some ability to communicate with the RAID card, and then the Zabbix agent itself can
it's APMI based.
It's IBM. So hardware-based hardware rate controller status is also through Zabbix agent. I
Yes.
think there's some.
Yes. So basically, for the rate controller, we have MegaRAID utility on the OS,
Okay.
and the Zabbix check that calls that and parses the output and reports back. So we can check for smart errors. We can check for like a RAID 10 with 6 drives and one is not active. Increased error rate, things like that.
Okay, thank you.
So we pull data from a number of in-OS agents, IPMI data, also SNMP from the switch side, Sflow as well. So.
Hi, do you monitor or somehow prevent users from sharing genome data over the internet?
Yes. Although the thing is, the researchers get access to the data based on the data owners. And once they get access to the data, they are responsible for it. So we run a shared responsibility environment where we protect the data that we host. But once somebody gets access to the data validly, they are responsible for protecting the data. Okay, so it's part of their, when they sign up as the researchers to access the data, they also sign up for protecting the data further. So if they want to give it to somebody else, we can't.
Yeah. I noticed you had collect-D on the list there. I'm just wondering, what are you getting out of collect-D that you don't get out of Zabbix?
Collect-D.
Collect-D, it's all Ceph metrics.
Just Ceph.
Essentially, yeah.
We have basically, so we have two Ceph Dockerized tools. One is based on Prometheus, and it came with its own Grafana dashboard, and one based on collect-D. One has, it's different visualizations based on the same kind of data sets.
Have you tried to sort of replicate what collect-D does just in Zabbix natively to sort of get one tool out of the list?
Yeah, we have a bit of a tool sprawl issue for sure. It would be nice to maybe pare down and consolidate a bit, but at the same time, I think the interface of Grafana is a bit friendlier, a bit easier to digest than what Zabbix gives you. But so I'm kind of torn on that. I mean, I want my cake and I want to eat it too. So we run both.
But again, we have the same philosophy, focus on the things that are broken and spend time on things that you can improve. But if it works, then do something more useful. So.
Any more questions? No? Thank you very much.
Thank you.